What if planets were intelligent beings? What? Sounds like some kind of sci-fi plot. But the idea of planetary intelligence is something you can read about not only in fiction, but also in a scientific paper in the International Journal of Astrobiology, which is published by the University of Cambridge. At first, such an idea sounds, to put it mildly, extraordinary. However, if you read what this article is about, it becomes clear that it's not referring to literally living intelligent planets like Ego in the Guardians of the Galaxy, but rather a form of planetary intelligence. Here they mean intelligence as a collective process on a planetary scale. The article is titled Intelligence as a Planetary Scale Process. Yes, it does require some assumptions and speculative thinking, but overall it's less extreme than it might initially appear. Yet still very intriguing. Among the practical aims of the concept of planetary intelligence is its application in the search for extraterrestrial civilizations. At the very least, the idea can offer a different perspective on the search for life beyond Earth. In my videos, I discuss the conditions necessary for life as we know it, exoplanets that closely resemble Earth, and various methods for detecting life. But today let's delve into this topic in more detail. How we can search for extraterrestrial life or even intelligent civilizations. We'll talk about biosignatures and technosignatures. We'll also explore how the concept of planetary intelligence fits in all of this and what it actually entails.
My name is Andrei, and this is Cosmos Elementary.
The search for life beyond Earth is indeed a complex and challenging endeavor. Despite decades of searching, we have yet to find anything that can be confidently called signs of life even within our solar system, let alone on planets around other stars. We can't be entirely sure, but if we were to come across, say, a jellyfish under the ice of Europa, or if extraterrestrials were to visit us and make themselves known in a clear and unmistakable way, that would certainly provide strong evidence of extraterrestrial life or intelligence.
In almost all other cases, if we find something that could be interpreted as signs of life, there is a chance to find some other explanation for it. And that has happened multiple times.
We can search for life beyond Earth in various ways. In our solar system, apart from remote sensing methods, we also have the capability to send robots to other celestial bodies and look for signs of life on site, which is what rovers like those on Mars are doing. But today we'll be discussing search beyond our solar system. Clearly, in this context, we can only rely on remote sensing methods, like trying to find any signs indicating the presence of life using telescopes, observing in different regions of the electromagnetic spectrum. Here another question arises. What kind of life are we searching for? Any form of life, or specifically advanced civilizations? And in general, what exactly should be considered as life? It's safe to say that there isn't a single absolute, universally accepted definition for it.
On a global scale, we can talk about two main directions in a search.
We're either looking for biosignatures, certain indicators in observational data that can be explained by the activities of living organisms. This doesn't necessarily involve intelligent civilizations. It's simply about the presence of some form of life on a planet. And there are also technosignatures. These are signs of technology, so their detection may already indicate a certain level of civilization. Now let's delve into each type in more detail, starting with biosignatures. When it comes to biosignatures, we have to be so-called carbon chauvinists. We are looking for signs of life similar to ours. Not because it necessarily has to be that way, but simply because modern assessments suggest it's more likely, at least because the basic chemical principles and laws of physics are the same everywhere. Take one of the key factors for our life, water, which is a good solvent and facilitates chemical reactions, although it has other roles as well. It's very common in the universe. Water consists of the most abundant element in the universe, hydrogen, and the third most abundant element, oxygen. Alternatives to water may require more extreme conditions and fundamentally different processes.
The second pillar of our life is carbon. which is necessary to build complex molecules of living organisms. It is also considered to be more likely than its alternatives.
It is quite abundant, and with it, a vast array of complex molecules can form. There could be alternatives, but it's considered to be much more difficult to form a variety of complex molecules with those alternatives.
But alternative biochemistry is probably a topic for another time.
In short, we can't entirely rule out that life on other planets could have fundamentally different biochemistry, but today it's considered more likely that life with biochemistry similar to ours could emerge. And of course, it's easier for us to search for what we understand. One important aspect of such a search is to look at our own planet, model how terrestrial life activity would appear to a hypothetical remote observer, and then search for something similar on other planets. Another important point to consider is that when we study planets that are tens or hundreds of light years away using imperfect equipment and limited methods, we cannot be 100% certain that what we find in the data, what we call a biosignature, is indeed a true biosignature, meaning it is genuinely the result of activities of living organisms.
And here there are two approaches. Either, knowing all this, we classify all of the potential biosignatures as false positives, because all of them could have non-biological origin. However, this approach may not yield much. Alternatively, we could classify all signals as potential biosignatures, but there needs to be a balance. We need to understand the limitations and search for alternative explanations, but at the same time, not to dismiss the possibility that the signal could indeed be indicative of life.
Even if it turns out to be more likely that it's not the case, in the process of searching, we can learn many valuable things. Biosignatures don't have a clear, universally accepted classification, but in one of the sources I used, they are divided into three main categories. Firstly, there are gaseous biosignatures. These are direct or indirect products of biological processes. A simple example is molecular oxygen, O2, which is produced by organisms during photosynthesis and is then transformed into ozone, O3, through photochemical reactions. By the way, how can we determine the composition of a planet's atmosphere when we often can't see it directly?
Well, in this case, as well as in others, when we need to obtain information about the chemical composition of an astronomical object, we use spectroscopy. And a brief reminder.
Light can be broken down into a spectrum using a prism separating its component waves of different wavelengths. And when we do this with radiation from, for example, an astronomical source, we typically see lines in the spectrum. These are dark absorption lines that appear in the spectrum when light passes through a substance, is absorbed by it, and then re-emitted, and bright emission lines that occur when we directly detect light from the radiation source. As many of you know, these lines are unique to the atoms of various elements and different molecules. Telescopes are equipped with spectrometers, spectrographs. When we observe objects like stars with a telescope, we obtain a spectrum, and that allows us to determine their composition. But in the case of planets, most of the time we don't observe them directly, although there are a few planets that have been observed directly. We receive light reflected from them, or in theory their own emission, such as infrared radiation. But in the case of indirect observation, which often involves transits when a planet passes in front of the star and blocks some of its light, we can obtain information not only about the planet's size, but also about the chemical composition of its atmosphere. During a transit, the star's light passes through the planet's atmosphere, if the planet has one. Depending on the composition of the atmosphere, certain wavelengths are absorbed, and in the resulting spectrum, we observe specific lines. That allows us to deduce which molecules or atoms are in presence in the atmosphere. A whole range of gases can be considered potential biosignatures. As I mentioned, these include oxygen and ozone, methane, a significant source of which on Earth is biological activity, is another. Nitrogen oxide is considered a strong biosignature because non-biological sources on Earth are relatively small. Several gases that contain sulfur in their composition are direct or indirect products of biological activity. There's also chloromethane and others. Of course, if we find signs of any of these gases, it's too early to conclude the presence of life. All of these gases can have non-biological origins. That's one point. Studying the atmospheres of exoplanets is a relatively new field compared to many other disciplines. So far, these methods have been used to obtain information about the composition of mostly gas giants' atmospheres.
But there are also known examples within our solar system.
When the Mars Curiosity rover discovered signs of methane in the Martian atmosphere, media made a big thing out of it, almost as if the discovery of life had been made. However, in reality, methane can be produced without the involvement of living organisms. Secondly, naturally, when we study objects that are so distant using indirect methods, there can be uncertainties and even errors in the data. So the very fact of detecting a potential biosignature can also be questioned.
Another well-known story combines both of those issues.
The infamous discovery of phosphine gas in the atmosphere of Venus. While phosphine can be produced by living organisms, there are also non-biological ways for its formation. Furthermore, the detection itself in the original study was not 100% certain, and the subsequent research indicated that there might be much less or even no phosphine present in the Venus's atmosphere, and this is just within our solar system. It might seem like discovering one type of gas, especially when its discovery is in question, doesn't reveal much, but it would provide more confidence if they were to detect several different gases at once. For example, having high-quality data on an atmosphere dominated by nitrogen, carbon dioxide, water vapor, and oxygen, in other words, an atmosphere with a composition similar to that of Earth. If such a planet is also similar in mass and size to Earth, and is located in a habitable zone around a star with moderate activity, then such a discovery becomes much more intriguing. But while the atmosphere can reveal a lot, gases are not the only biosignatures. The second type is surface biosignatures. When we detect light reflected from a planet's surface, the characteristics of that surface can also be reflected in the spectrum we obtain. Light can directly interact with biomass, such as pigments in the ocean or vegetation on land.
In any case, our telescopes are far from being able to resolve disks of planets. We observe them only as points of light. In other words, the signal from biomass should be visible in the average spectrum of the planet's disk.
So far, the only known and well-studied signature that leaves a unique imprint of biological activity in the average spectrum of a planet is known as the red edge. This is a special property of how light reflects off vegetation. Chlorophyll in plants absorbs most of the light at certain wavelengths, and at specific wavelengths, its reflectance sharply increases. This characteristic can be observed in the spectrum, making it a good biosignature.
And the third type is temporal or time-dependent biosignatures. These are features that change over time and could indicate the presence of the biosphere.
Both gas and surface signatures can change over time, for example, due to seasonal variations. For example, during a year, the concentration of certain gases. A simple example is the change in the levels of carbon dioxide in the Earth's atmosphere due to lower temperatures and sunlight during the winter and reduced biosphere productivity. Similarly, with the changing seasons, the reflectivity of the planet's surface changes. Bioluminescence can occur, and so on. Changes can occur not only seasonally, but also throughout the day, or the biosphere may respond to other factors that can theoretically be identified and linked to those changes.
It's clear that there are many nuances here. Not all the changes could be recorded, but it also depends on the perspective from which we observe the planet and other parameters, and this type of biosignatures is the least studied.
As I already mentioned, study of exoplanets' atmospheres is a young discipline. Much hope is currently placed on the James Webb Space Telescope, which has already provided some interesting results. Having just one individual biosignature won't be sufficient to draw conclusions about the presence of life. However, if multiple biosignatures from different categories are detected on a single planet, we potentially can remotely identify a planet that closely resembles Earth. This would be based on the combination of gases in the atmosphere, surface data, and temporal variations.
Next, we have technosignatures. These are certain features that could be detected through astronomical methods and could be the result of technologies on other planets or in other systems.
The most extensive, long-term and systematic search for not just life, but specifically advanced civilizations are primarily conducted within the SETI initiatives. It's predominantly research in the radio spectrum and attempts to detect signals of artificial origin emanating from other worlds. So far, decades of SETI research have not yielded any confident results, but this doesn't mean that we are alone in the universe. While it may seem that our research has been ongoing for a long time, in reality we have only listened to a small portion of the galaxy.
Here sometimes people draw the following analogy. If we were to compare our galaxy to an ocean, then we would have only scanned the volume roughly equivalent to a small swimming pool.
People often discuss that even in the already scanned area we could have missed something. After all, another civilization may not necessarily use radio for communication, and there are many other nuances. Megastructures is another type of technosignature that we could potentially discover. Most often people discuss various types of Dyson spheres, hypothetical massive structures around stars. The most famous case here is the story of Tabby's star, which exhibited noticeable and seemingly too pronounced periodic dimming. And among the explanations for this was a hypothetical megastructure. But today it is considered more likely that the star's light is simply being blocked by dust clouds or debris from a destroyed planet or a moon. Also, in theory, we could detect artificial lighting coming from an exoplanet, for example from cities during the night, or additional heat generated by the technological civilization.
But perhaps one of the most realistic scenarios for technosignatures, from the perspective of our ability to detect them, is atmospheric pollution.
So here we can apply the same methods for studying the atmosphere that I described earlier. In its composition, we could find not only biosignatures but also gases that on Earth get to the atmosphere through human activities, various byproducts of industry and technology.
If we find signs of such gases in atmospheres of rocky, Earth-like planets in habitable zones, and if those gases do not naturally occur on Earth or are extremely rare, that could be a strong technosignature.
For example, recently there was a study that focused on chlorofluorocarbons, CFCs. On Earth, significant quantities of CFCs are only produced in industrial processes. They have been used, for example, as refrigerants or cleaning agents. After their widespread use in the 80s led to the formation of the ozone hole in the Earth's atmosphere, many CFCs were banned internationally. However, they can still persist in the upper layers of the atmosphere for a long time. In the article, scientists were studying whether James Webb could detect such substances, and they concluded that under certain conditions it would be possible. For instance, if the star is not too bright and the starlight doesn't overwhelm the signal from atmospheric pollutants.
In general, if we find such substances in an atmosphere of another planet, it could reasonably suggest the presence of technology and an advanced civilization there, who, just like us, may be destroying their planet's atmosphere. And here the question of the planetary scale intelligence arises.
So we are attempting to find intelligence beyond Earth. However, typically in this context, and not just here, intelligence refers to the intelligence of individuals. But what if we expand this idea and consider it as a collective property that operates on a planetary scale? That very planetary intelligence. This is precisely the question raised in this paper. Furthermore, there is a discussion about whether a transition to planetary intelligence has occurred on our own planet and how such a perspective on things can aid in the search for extraterrestrial life and help address global issues here on Earth. So what is meant here by planetary intelligence? In the case of Earth, it's primarily about humans. Each person possesses intelligence, knows how to use tools and develop technologies, but What if there is something that can be also called intelligence, but it is not inherent to individual representatives, but to the entire collective, and it functions as one system?
Here, the authors draw some analogies with other organisms. For example, some social insects, microorganisms, slime molds exhibit something akin to collective behavior.
Slime mold are groups of organisms that, together in the search of food, establish optimal paths and essentially solve mathematically complex spatial problems. In one of the experiments, a slime mold species recreated a complex railway system pattern of Japan. We could also use trees as an example. According to some studies, the roots of trees in the forest connect through an underground mycorrhizal network, a symbiosis between plants and fungi. And if there is a deficiency of nutrients in a particular part of the forest, a signal can be sent through this network, and nutrients are delivered. Here one can view the forest as a self-sustaining system. So when it operates as a system, when the whole is greater than the sum of its individual parts, we can speak of planetary intelligence. And intelligence is not something that arises on the planet and exists independently, but rather what happens to the planet itself becomes one of its important attributes, changing the planet itself.
And this may seem strange, but something similar has already happened here on Earth. The emergence of life on Earth, not even the intelligence, just life itself, had a significant impact on the planet.
When organisms learned to photosynthesize, it had a global impact. The composition of the atmosphere changed significantly. The climate shifted and a great diversity of organisms emerged, gradually becoming more complex. These are the kinds of changes that a hypothetical extraterrestrial civilization, if they were observing Earth for an extended period of time, might be able to notice. How the atmosphere has changed, the properties of the surface and the activity.
These global changes are linked to the biosphere, but when discussing intelligence, the authors introduce another term, the technosphere.
And here, for a habitable planet, they propose 4 stages of development. The first stage is the immature biosphere. This is the state in which our Earth was billions of years ago, when microorganisms had already appeared, but there were no plants. The biosphere had little influence on other planetary systems. The second stage is mature biosphere. For Earth, this is a period from 2.5 billion to 540 million years ago. Stable continents emerged, plants evolved, photosynthesis began, oxygen accumulated, and the ozone layer formed. During this stage, the biosphere had a significant impact on other planetary systems. The third stage is immature technosphere. According to the authors of the article, this is the stage we are currently in. Our civilization and technologies exist, but the technosphere is immature because it's not integrated into other systems of our planet. We use the planet's resources, generate energy, and this mode of operation may not lead to positive outcomes. The fourth stage is the mature technosphere. Technologies serve not only us, but also work for the benefit of the planet. The technosphere coexists with the biosphere, and both thrive, much like trees and mycorrhiza exist in symbiosis. What the authors refer to as planetary intelligence is inherent to the fourth stage. This is the exact definition from the paper. Planetary intelligence is the acquisition and application of collective knowledge operating at a planetary scale, which is integrated into the function of coupled planetary systems. This is a new system that is not just composed of the minds of individual people, but that operates on a more global scale. As a result, new properties emerge on a global planetary level. Feedback systems between the technosphere and the biosphere are established for self-regulation and the preservation. It's clear that, as of now, we don't have this on Earth. But there have been individual examples, and one such example I already mentioned is the ban of CFCs when there was a risk of ozone layer depletion. Indeed, there are many such problems. The threat of global warming is a significant one, and the measures taken so far are not entirely reassuring. In accordance with the logic of the authors of the article, for the continuing existence of the planet, it should transition to the next fourth stage and acquire planetary intelligence. The question, of course, is how to achieve this. Now, how is this related to the search for extraterrestrial intelligence? Let's suppose we could find life even without an intelligent civilization through biosignatures. Among technosignatures, as I mentioned, we could detect substances like CFCs. So we are searching for a civilization that, like us, has not yet integrated into the functioning of the planetary systems and is still damaging its environment. But according to the authors of the article, it's more likely that other civilizations should be older than us. And if they, like us, continue to have such an impact on their planet, they might have eventually destroyed themselves and not transitioned to the fourth stage. Or they could have already transitioned to the fourth stage a long time ago. In the first case, we might not find a civilization even if it once existed, because it may have self-destructed. In the second case, the civilization has transitioned to a different level, and in their atmosphere, the technogenic emissions we are looking for may already be absent, as they've evolved beyond that stage. Understandably, there are many assumptions in all of this, but the general conclusion is that potentially other civilizations could possess planetary intelligence, and it may be necessary for us to reconsider our ideas about the way we look for technosignatures, because in reality, they may turn out to be not what we are currently looking for or planning to search for in the near future. Even in the history of our planet, substances like CFCs would only be detectable in the atmosphere for a minuscule portion of a civilization's existence. If someone were searching for us based on such a sign, the chances of stumbling upon us during this small window of a few decades would be quite slim. In any case, when searching for extraterrestrial intelligence, we use ourselves as the only known example, and it's not necessary at all that another civilization, if it exists, should bear any resemblance to us. But who knows? Perhaps even if it's vastly different, one day in our search we might stumble upon something unmistakable for anything else that points to another extraterrestrial civilization.
Thanks for watching the video. As usual, links to all of the sources are down below in the description, and if you enjoyed this video, go watch some other videos on my channel, leave a like, comment and subscribe. Bye!